welcome back. Last class from my side. I still have to talk about two different subjects, a little bit different from before. Still speaking about my kind of network, the kind of operation that I have to add to them in order to make them even more interesting, or the kind of operation they can do. So they're going to be a little bit beyond quantum network, and we're going to speak about some more computing based algorithm kind of machine learning. So start with non-Gaussian elements. So the last three classes I've been speaking about how nice are my network, because I can easily generate in lab. I can do it in a scalable way. I can do teleportation protocol. I can do a communication protocol. Still, if I can have some non-Gaussian statistic in it, could be very nice. And for doing it, I need to have some hints on linear optics at first. So I think it's the third time I show this slide, which is really, the idea of my system that produce multiplexed state. And I was telling you yesterday that at the end, actually, we have two different setups in which we have a single pulse generation of this multiplexed system. And the one at telecom wavelength works better than the one at near infrared. And the reason why is actually just because you're in a regime where, the multimode nonlinear optics is good for what we do, in the sense that another way of giving you the general Hamiltonian, so this is more based on a continuous framework of wavelengths. So it's exactly the multimode Hamiltonian I was giving yesterday, but instead of having the sum of specific metrics, here you have the integral of a function. And this function is nothing else the joint spectral amplitude for the parametric down-conversion process. That could be that some of you already have seen when you look at the parametric down-conversion process in order to generate a couple of photons there, okay? And it's a composition of the phase matching function. So this is really very much related on the crystal that you use. And that the pump shape is the instruments, like the tools that I had in order to shape this GSA. So the way we look at it, in order to look at the multimode structure, could be also that you do some Smith decomposition. So I think maybe all of you already had about the Smith decomposition. And very often you introduce Smith decomposition for discussing about entanglement. And actually, when you look at entanglement correlation between photons that are produced in this spontaneous parametric down-conversion process in these two channels, is exactly why you use this Smith decomposition. And this Smith decomposition is giving me exactly the equivalent of the Bloch-Messier decomposition for the continuous variable system. For this specific system, we get exactly the same decomposition. On one side, actually, is the decomposition of the quantum state that you want to do in order to see how much is entanglement. On the other side is decomposing the multimode terms that are the one that giving you the squeezing at the end of the day. And well, the fact that we can measure many more in this condition is because actually the mode that we got in this telecom setup are not too much large, even if I use a long crystal. So this is really driven by these two terms. And so I can measure with my homodyne detection. So this was the idea. Now, keep in mind this, because we're going to use later on. And we're going to use later on because I wanted to use some non-Gaussian operation in my system. So I have a system that is spectrally multiplexed. So I would like to do some operation on very specific node of my network, if you speak about nodes. So I want to add a non-Gaussian statistic of quadrature. Why I want to do it? Well, it's something that a lot of people look at because it's really the one that gives you the hope of having some kind of quantum advantage at a certain point for computing task. And I want to control on which spectral modes I can have my operation. So the two that we have been looking at are photon addition and photon subtraction. I think I have discussed with some of you yesterday, telling I have done photon addition, photon subtraction all my scientific life long. That can be done in a selective way in nonlinear optical processes. And in particular, what we are recently looking at is how to engineer them with in waveguide processes for working in the telecom regime. This is one where we have the best results. So one slide on what it is, photon subtraction, and what has been photon subtraction in the last more than 20 years in the quantum optics community. So the idea is that you want to subtract a photon from a beam, and the way it has been realized, and you can sketch in any case, the fact that you can use a beam splitter. There is a high transmittivity. So sometimes in the reflected port, you have a photon that go out, you detect it. So you post-select on the fact that you have subtracted a photon on the transmitted path. You can have a description with an operator and an Hamiltonian. And normally, actually, this theta value that you have here is really linked on the reflection coefficient, so it's very small. So actually, what you apply on the two mode fields coming on path A and B is this one. And then actually, you project on one of the two on the fact that you measure one photon. And this is just the very typical calculation of what is going on this path. Once you have detected one photon on the first one, given the probability that you have to detect this photon. And it works. I mean, this is something that has been used several times in order to go from a Gaussian a Wigner function to a non-Gaussian and negative Wigner function. Okay. So if you want to be mode selective, what you have to do? So at first you have to consider that you have a multi-mode state coming on your system. And actually, if your system is multi-mode, at least in terms of frequency, you cannot do with a linear optical process. You need to have a nonlinear optics. It's exactly because you want to transfer specific amount of energy from one frequency to another. And this you cannot do in optics with a linear process, okay? So the way of doing it is you use some frequency generation protocol where you can, I mean, on one side you have your system. So this is the system that generates. So in one beam, I have my network, my entanglement network with different frequency. Is coming at the crystal with another signal, a coherent beam is named the gate. And sometimes you have up-converted photon that is at the sum of the frequency of the two beams here. So it means that actually, if you see a photon here, you have subtracted a photon from this one. Okay. The way you want to do it is to engineer the nonlinear optic operation such that the mode of the gate of the classical beam is going to choose the mode from which you subtract the photon. Okay. So you see that here you have again a kind of Hamiltonian, a multimode Hamiltonian. So it is the, let's say, it's the multimode version of this one, where you have what in this case is called a transfer function that depends on, here actually the one of the incoming being is classical and is take actually the place of the pump of the parametric process as an envelope that you can work with. And then actually you have this term that's linked, how much is efficient the fact that you transfer one photon from the signal beam to the up-converted photon. And you can, this process can be decomposed again with a Schmidt decomposition. And actually what you would like to have for this process is to be single mode. So meaning that if you calculate what is called the Schmidt coefficient, in a way telling how many of these coefficients you need to. So when you use the Schmidt decomposition to look at entanglement configuration, is giving you the degree of entanglement that you have. Here actually is giving you the amount of being multimode or not. Okay. And you want to have only one mode that come out from this system, because this is the only way that you can really guarantee that every time you select one photon, well, the mode shade that you have put in is selecting specifically one mode from which you subtract. I will give you a picture of it that probably is going to be more clear than what I'm telling, and I think it's going to speak a little bit better. Before going there, just to tell that this process has already been done in our lab some years ago, meaning that if you send the beam where you have your multimode system, and here I'm describing my multimode system in the basis where it's diagonal, so where I have a multimode squeezing. I can always do in the sense that I can always measure here with my homodynamic detection by looking at this single mode. Let's see that I squeeze if I don't do anything. If I get a specific click here where I have put a gate with a specific shape, well, I still can measure the Wigner function for these independent modes. And then you can see that you can select the one that you want to be negative here. Something else can be done by, if I take a cluster structure, and now taking a cluster structure, you know that it means that I consider 4 different modes that are a combination of the initial modes, and they can always choose to look by homodynamic detection at these individual modes. And then I can send a gate that corresponds to the shape of this node here, okay? And then actually I can subtract a photon from this node. So you have a 4-mode continuous variable system that in principle actually now is not enough to look at covariance metrics because you have non-Gaussian state of light. So what you would like to do is a full optical homodynamic tomography of your system. Well, 4 modes is already too much. You cannot do. It's taking ages. It's really the limit. Okay. So at that time, for this paper, what has been decided to do is just to look at some non-Gaussianity of the quadrature distribution. So by looking at excess kurtosis, you can choose whatever you want. Was a way of looking at differences between the different nodes. And probably, I mean, is a little bit hard to see by looking at the shape. What came out from this system is that if you subtract a photon from this node, the one that is mostly affected is not this node, is the one on the other side. And now actually we can do the theory for, I mean, especially for this very small system, why, but well, let's say that it's a little bit more difficult to generate, describe, at first characterized non-Gaussian multimode quantum state. I was telling that in principle, if I really want to see what is going on here, I need to do the full tomography because covariance matrix is not enough anymore. Okay, so just having the experimental characterization of the state, and then very general, telling you what is going on is a full life career that is doing my office mate that is really looking at entanglement of non-Gaussian state. Characterize them, describe them, telling what it is, telling you where is the Wigner negativity, how you can describe it, what is the maximal amount of mode you need to describe the system. Because here I've done something that is a local operation, okay? But then you see that actually it affects the one on the other side, okay? And from them, I mean, we wrote a bunch of other 10 papers about how you can characterize theoretical and experimental this kind of state. So this is the reason why actually non-Gaussianity is interesting, because it's more complex, and especially if you go in a multimode system. And actually the fact that you can really decide on which mode you act with this specific kind of symbol operation, well, it's not easy to describe in general. Okay, so this is the speech for the non-Gaussianity. And then actually I'm going to the second process that we can do, that is the single photon addition. is also a process that transforms Gaussian state in non-Gaussian state. And these you can only do with nonlinear optics, even if you're single mode. And actually it's exactly a parametric down conversion process. So it's a parametric amplification process. So is the same Hamiltonian that we have used for generating, but here is the single mode case. So actually what you do is that you have your signal on one path, and then every time you see another photon, well, you know that you have added a photon on this path. And if you go multi-modes, same thing actually. So this is very, very closely related to the first Hamiltonian I was showing for generate multi-mode squeeze state. Here I have the phase matching function and the pump. I can do a Smith decomposition. But again, in this case, I want to be monomode for this specific scenario because I want to be mode selective. Okay. Again, if this does not speak you too much, it's going to be clear when I show some picture of the ideal case that I would like to look at. So the recent work that we have done in this case, that we want to be able to manipulate the mode structure and from where we subtract of where we add the photon by looking at some waveguide materials, and also looking at the thin film geometry that is very much promising in terms of functionalizing your system. So this is a work we have done in collaboration with the group of Christine Siberor. So now, what is the famous ideal case that I would like to have? So what I'm plotting here is the joint spectral amplitude or the transfer function I was showing before for the signal fields and the upconverted fields, okay, in the photon subtraction case. And here I'm showing the joint spectral amplitude for the signal and adder, okay? In a way, what you do is that at first you make the picture of your phase matching that has some shape in this plane, given the different wavelength that you can have for the two different beams. And then you can add the two, let's say, classical envelope, that in one case is the gate, on the other case is the pump, that act on diagonal term, because actually it depends here on the frequency of this photon minus the frequency of this photon, and here it depends on the frequency of this photon plus the frequency of this photon. And the region where they intercept are defining actually, well, the shape of your process, if you really want to see the shape on this plane. Or if you want, actually, this is the one that is filtering out the mode where the process is going to happen. Actually, what is going on that here, for example, I'm sending a Gaussian gate, and here I'm sending a gate that is Hermite 01. So that you see actually is as this shape also in the diagonal. And you can see actually that if you project these with these, you get this shape on the signal. And this is actually is the mode from which you subtract the photon in this case. And this is the same actually for the single photon addition by transferring this mode function through this phase matching. I can select the mode to which I add the photon, okay? And this works because the phase matching has this strange shape. So I don't know how much you know about phase matching, but very often on this picture for parametric process, you have some kind of banana shape from the very beginning, okay? So this means that you really have to work a little bit in order to get this non-symmetric shape. If you are kind of people that have been working a little bit to get a parametric down conversion process that directly give you a pure single photon without filtering on the other channel, for example, is exactly the same kind of shape that you have to look for in the case of single photon addition. Okay, so the physics is there. Then what you have to do again is that we were running some algorithm in order to do the reverse engineering, meaning that we have the parameters that are given. So in Paderborn, they're working on the fabrication of this kind of device, so they know the parameter that drive actually a linear Hamiltonian. What we can modify are parameters like, for example, in this case, are these G, H, and an angle parameter, or this distance. So this is actually taken as a reference in order to see if our reverse engineering problem works, because this is the kind of system for which you can find easily a solution. Well, the idea is to look for the good phase matching. And actually, these are a bunch of results that we found that are not bad. So this is for the kind of reference system geometry, which is the metallic waveguide approximation, where you see that this K value is really the one that is, is the Smith value that is giving you how much you can be selective if you really want to select a mode and start to be close to 1. So these are the shape of the modes to which you add a photon in this case, given that you always see the photon on the other parts on the same mode. So the important point is that maybe you have other geometry that are going to, where actually the modes in which you subtract or add the photon for the signal depends on the shape of the pump or on the shape of the gates on the other case. But you want to be in a condition where you never change the shape of the heralding field. Okay, you always want to have some heralding field that is Gaussian, spectrally, spatially. So meaning that you want to put your detector there, and you want to take care about filtering spectrally or spatially the modes at which you herald. So you want to have this, and this is very clear when you speak about transfer function in the photon subtraction. You want to transfer the function of the pump on the function of the signal from which you subtract a photon. Okay. And then actually we also have the results for the thin film geometry. And so this is again the single photon addition, and these are the results for the single photon subtraction in the case of metallic waveguide and the case of the thin film geometry. So this is a theory paper on reverse engineering in order to get the good parameter in order to control this thin film. I mean, they're not fabricated yet. What is really interesting is that for a long time, we're trying to see a feature for the diffusive waveguide in order to do this operation at telecom wavelengths, and we couldn't find. So the idea is that behind this thin film structure, it seems that you can really gain in parameter control in a way that you can really manipulate the system at this kind of wavelength. Okay, so I'm not going through the, except if you are expert on the kind of parameter that you can have in this structure. I'm not going really through the full details. Do you have questions up to this point on this part? Because I'm going to switch on another subject. Yes, no? Okay, very good. Last part. The title of this part is A Reservoir for Local and Distributed Process. So I'm going to speak about a bunch of protocols that we have devised and in collaboration with a group of Roberta Zamrini at IFISC. That is about reservoir computing. So here you also have one specific feature on variational quantum algorithms that is collaboration with Paolo and Federico that were at ICFO both at this time. So the interesting part of, I mean, the interest of this part is that I would like to have some kind of NISC protocol. So I think this also came as a discussion probably yesterday. So how far you can go in order to get the full stack structure in order to do fault tolerant quantum computing in the system. I was telling you, I mean, the results are very exciting. Still, we are not there actually. So, but probably we can devise some protocol that is less demanding in terms of resource, and probably also some that is fully adapted to our scenario. So in particular, so the group of Roberta, they work on reservoir computing, quantum reservoir computing in many different scenarios, and we devise experimental and theory that are really dedicated to the continuous variable setting. And the bunch of papers I'm showing here just use Gaussian resources. Okay, so probably you tell, I mean, you're thinking, well, you have told that in order to do some computing, you need non-Gaussian stuff. Okay, so this is a specific scenario in which, of course, if I go non-Gaussian, very probably I can have something that is very much better. But still is a condition where quantum Gaussian can be better than the classical. We have to very specifically define what we are speaking about, also because, I mean, I'm not a full expert of machine learning protocol here. I think in the audience, there are people that are more expert than me, but you have to be very careful what you're speaking about and to which kind of classical protocol you're comparing with. By the way, so the first result that we had in this scenario, so first of all, how many of you already know what is a reservoir computing? I know there are two here in this row. I'm not speaking to you guys. For the rest, yeah, probably not so many because it's a quantum network school. It's not a quantum reservoir computing school.
What is reservoir? Reservoir is a network.
Yeah, so it was beyond the quantum internet. So already spoke about quantum internet. So and now I can speak about reservoir computing. So this is a sketch of a reservoir computing protocol that, I mean, is very well defined to approximate time series, okay? So you want to learn time series. A way of featuring it that is you have a network like in neural network. The difference between reservoir computing and neural network kind of protocol is that here you are not training the network itself, is the reason why it's called a reservoir. And you just train, if you want, the last layer, mainly how the last layer is connected with, I mean, you as classical system in the case of quantum that you measure. And so very often, I'm not going to go into this debate about if you have reservoir computing on extreme machine learning. So we take, I mean, I follow what is the definition that Roberta uses, really the one where you need to have also, is a system that has memory of the previous system, I mean, of the system at the previous time. And this is actually one of the features that you want to build in order to be able to learn, for example, chaotic series. So, I mean, it's very interesting because you can learn, I mean, if you want to sell it, so is the usual kind of selling that you can have also for quantum computing. Of course, you can predict a chaotic system, stock market, on this kind of things. But, well, it's very much specific for learning time series. So here the idea is that you have this system, you have a reservoir space that in our case is our network. So it's our network of harmonic oscillator, and then you have, I mean, it's a Gaussian network with entanglement correlation and so on. And you input your input, so this is, you have a series that is coming by embedding this input in a parameter, in a physical parameter of your system. Then you read, and very much in this case, the reading is done via the measurement that we know, that we do very much in a good way, that is homodyne detection. And then actually you have, a learning, as kind of calibration of the output corresponding to the measurement that you do, that should correspond to the target function. So what you want to learn is a function of the inputs coming. And the fact that you have only the training of this last layer is that very, very often, the training is done via linear regression. So it's not very much resource and time consuming. So this is why actually is nice. So this is very general, for the reservoir computing. So in this work, what we have done is that we have shown that reservoir computing is universal in the case of Gaussian harmonic oscillator. I'm speaking not about quantum reservoir computing in the sense that it could be quantum computing. So this is, a classical task, but the classical task can be done in this scenario by using just Gaussian resource. And in particular, we were trying to embed the incoming series in parameters that are parameters of the quantum states of this harmonic oscillator. And the setting was to look at thermal, squeezed, and coherent states. Okay, so the idea is to look at the border between the classical and the quantum world. And then you can set results and compare to the kind of classical system that I use for performing reservoir computing, using this capacity. So this capacity, information capacity, is a way actually of measuring how much efficient, if you want, you can picture us being inversely proportional. It's not exactly like that, but let's think about it, inversely proportional of the error that you do in learning the function. And you see here appearing different colors, because actually you can learn more or less nonlinear function of the input. And here you see that the efficient learning, for example, in the case of squeeze state, where you encode in the phase of the squeeze state the incoming series, is very much efficient for polynomial of high degree. So actually what you want to learn, so the task to learn is that you have a series coming and you want to learn a polynomial in time of different degree of this series coming. And this is a way of quantify how efficient you are. And the way you do it is that you encode the incoming parameter in a physical parameter of your quantum state. And you can use coherent state or squeeze state, and then you can see that actually the information capacity is different. Okay. So here you have an advantage. I don't want to call it, we can discuss, I think, a long time on what is quantum advantage. But this is a specific system, actually, when you compare to thermal state, or even with the classical system, actually the squeeze states are more efficient in performing this task. Second point is that, so this is actually the, let's say, classical scheme that you can have in a reservoir computing protocol, where you encode the external inputs into the quantum substrate, you let the quantum reservoir evolve, then you measure a set of observable, and then you approximate the task. So this is the protocol is repeated for the following input for the full sequence. Actually, we decide to devise a measurement-based continuous variable reservoir computing. And I'm showing it because now you can understand it, given the lecture that I have given yesterday. So what you have here, so probably you recognize the same structure that you can have for the teleportation gate here. No? You have your on physical state, so this is still theory, coming with a zero value of P. Here, the incoming inputs, in this case, actually is a specific, is the reservoir frozen at a specific time. You have an entangling gate between the two. And here what you do a measurement. And the measurement is the one that depends on the input of the reservoir, okay? At each step, what you do is a quantum teleportation, meaning that actually, of course, you do the measurement, so something is happening here. And what is here, you send to the next step that is going to be exactly like this, and partly you measure it, okay? But you need to measure because you need to acquire information if you want to learn the function, but you also need to re-inject the system in order to keep the memory. So what exactly, so this is the case where I can tell you what is this measurement without being the measurement of exactly a P quadrature. What you measure a quadrature that depends on P plus Sx. And this has the effect that actually on the output state, you apply this phase term that depends on Sx squared. Okay, so this is a typical case where I apply the teleportation gate with a specific measurement here. The idea is that you want to use multi-mode, multi-stack structure where you have several of these 0p state coming. And if you recall, these are the ones that at the end of the computing in the universal quantum computing scenario for continuous variable, the one that compose the cluster. So actually you can do it in parallel, having several inputs and having several nodes of the cluster coming in order to have a multi-mode realization of it, and is a measure-based protocol because instead of embedding actually the incoming series in the parameter of the quantum state, you embed in the basis of the measurement that you do. Same way you will do the computing in the universal quantum computing. And then here, the idea was to test a specific task. So this is a temporal XOR, so XOR done with an input and the following one. Here you have a typical test that is done with reservoir computing, which is the NARMA D or N, meaning that you have function you have, in this case, UK is the input series, and YK is the function that you want to learn of this input series. And you see that actually depends also on previous results for the function itself at different time. Okay, so these show actually that you can have or cannot have memory in the system, and you can learn actually function of the time that is previous time. Okay, so this was the results for it is still theory, and to finish, I'm going to finish very early actually. You see, but I think they're going to be happy for it. Sorry. Exactly, but I think also because I really explode my time yesterday, so they can be saved today. I want to give an experimental result because, what I have speaking about up to now were theory. So you can tell, okay, again, you're devising a theoretical protocol, but probably you're not able to do in the lab. And actually, this is a very recent result on the implementation of quantum reservoir computing protocol in the kind of system that we can do in the lab. So all along the last 2 days, I have been speaking about this system. Okay, what you have here is the waveguide that is producing different modes that are squeezed. Okay, I want to encode my input series. So what I decide to do is to shape the pump of my parametric down conversion process. So the easiest way to do is just, if I consider just one parameter arriving, I just give a global phase, an electro-optic modulator. So this is what you call the global phase protocol. And then I measure with my homodyne. I was telling you that we're interested in implementing memory in our system, that the kind of reservoir protocol we're interested in is the one where we can have memory. So in optical system, memory is a little bit not easy to have directly on the system itself. So what you can do is that you reinject. So here is what we call an incoherent feedback, because we have measured the system and we inject the measurement as a feedback on the parameter that control the system itself. Coherent feedback could be done by measuring partially the system. So you can think about putting up a splitter and then you measure with an homodyne detection. And the second arm of the splitter is redirected into the system itself. So actually have an optical feedback with the quantum system going back. So this was the simple version that I was showing at the very beginning, where actually there's several implementing by having a function that should be nonlinear of the previous reservoir, but all the reservoir at the previous time and the arriving series. Actually, here we devise a little bit more complicated. So what you have is that if you consider, so this is the covariance matrix of my system, is changed in a way that depends on the value of the pump, that the pump depends on the incoming value coming, but also on the measurement that I have done before. And this is the way we implement. So the idea is that in this system, we have two things that we can control. One is the shape of the pump. So in this particular specific system is the global phase. And on the second point is that we can control the measurement. So we can control in which basis actually we're going to look. So if the squeezing, I mean, to give you the idea where is the resource of the quantum resource of this system, is that if the squeezing is in this mode set, and you measure, for example, in the frequency, what we call the Frexel basis, in this basis, you're going to, exploit the entanglement of the system for doing the computing. And here you have the results of, okay, before going there, there is a more, let's say, powerful way of injecting the parameter that allows to explore a large parameter space, is the fact that you can shape the pump in the same way you shape the local oscillator and to select the mode. And these allow you to encode different parameters on the different frequency of the pump. And this is the one that gives us the full control of the entanglement structure. And this is actually the way in which you can see that you can have an advantage compared to a classical case. So these are a bunch of results. So this is our the XOR on time domain. This is the prediction of a specific chaotic series. So you have the target and the predicted one, and then I want to show. So this is actually is a figure that we are going to correct in the. I mean, I couldn't put the corrected one because the paper is under revision, but. At the end, we found that the quantum system is better than we thought to be. So in the case where we do the full pump spectral shaping, so what I'm putting in this figure is the rank of the parameter that I can control, given the number of parameter. So is the expressivity of the system, meaning how many parameters I can have at the output that I can use actually to reconstruct my function, given the number of parameters that I control in my pump, okay? And here you have the difference between n equal 1 and equal 5, n equal 1, it means that I'm using the global phase, meaning that I'm just setting one parameter for my pump. N equal 5 means I'm setting 5 different parameters. And the shape is quadratic. I mean, you see that here is saturating, but it's saturating because actually you look at the output parameter given the number of input parameter, but we were limiting the number of input parameters. So this is why actually we limited the number of output. And in new calculation, we see that we can really go to the limit of the saturation. This is quadratic. You can do the same protocol by taking the same system and do what is called the spatial multiplexing, meaning that you do actually, it's like doing the same protocol with n equal to 5 parallel systems that are not entangled with each other. And actually, this is going to be very much less efficient than the case of n equal 5, meaning that, for example, we were seeing that, well, you can get the same results, but for getting the same results, you need to have 15 different classical reservoirs compared to the one that is quantum with 5 modes that can be controlled in the pump. Okay, I think I'm not going too far because it's not really the topic of going at this quantum reservoir computing. And I'm going to finish here, so you're free very much early today. Have any question? You're welcome. Yeah.
Surely it's not possible to ever do like a fully coherent measurement, right? Because you always have to siphon off some of the state.
Sorry, again?
Surely it's not, you know, you said like with this measurement, right? Like when you just feed back the result, that's incoherent.
Yeah.
But then if you have a beam splitter, right, then only a partial amount of the state will go back.
Yeah. I mean, yes, of course, actually, this is if you want, is the reason why we call it incoherent feedback, because we are not feeding back the quantum system. It's the measurement of the quantum system that control the parameter for the next one. Probably you can gain something, actually, we already had the calculation, telling that you can gain something if you do it with a bit splitter and feeding back the optical path. Gaining something more, it means that you have to go in the scenario where you really use the full stack of the cluster case with the measurement-based implementation.
Okay, thanks.
Yeah.
Actually, it's about the first half of this session, like, you know, subtraction and addition. So yeah. Yeah, actually, you know, I think I understand the concept, but for example, you know, subtraction seems to be much clearer than just adding photons to the system, because subtracting just means like detecting photons from. So my question is, I know that both operations have the effect of generating non-Gaussian CV states to the system, but are they like, you know, for example, some states generated by addition are in some sense quantitatively or qualitatively very different from those generated by subtraction?
Yeah, it's a very good question. Actually, it depends what you're looking for, the fact that one is better than the other. For example, the photon addition always generate, in the case of pure state, always generate Wigner negativity. It's not the case of photon subtraction. But photon subtraction is less non-local in a multimode state, meaning that this game that I was playing before with the squared cluster, where I subtract on one node and I get the most of the non-Gaussianity on the other, is because I'm doing photon subtraction. If I do photon addition, the most of the, let's say, effect, non-Gaussian effects, is given in the node itself that you are looking at. So it depends. Are you interested to have a big local effect, or you want to have and a local effect that actually, I mean, the rules of the game is not really the fact that you have entanglement within the two nodes, but is steering between the two, is the one that is governing if you can have an effect done by one to the other in this system. It also depends from which state you start with. Of course, for example, in squeeze states, if you keep adding and subtracting photon at odd number, you don't really see a lot of difference for n, I mean, at the n equal 10 step in photon addition or photon subtraction. You're degassifying, and at a certain point you get something that is very much similar. So that could be one way of answering the thing. We can close the session, I guess. I did my duty.
Thank you very much for your excellence.
Thank you.